Welcome back. In this section, we're going to start looking at solving logarithmic and exponential equations. We're going to begin with the exponential equations, starting with sort of the easier ones to work with and make our way up to the more difficult ones to solve. And then we'll do the same thing for the logarithmic equations. So starting off with the easiest kind, which is if you have an exponential equation and if you can get it into this form where it's one exponential function equal to another exponential function with the same base, then you can say since you have two exponential functions with the same base equal to each other, then the powers must be equal to each other. The important phrase here is can be written. It might not be that the equation already has them as one exponential function equal to another, and they might not already be in the form of same bases. But if you can do a little bit of work with your exponent rules to get it into that form, then that's probably the easiest way for you to solve an exponential equation. So let's take a look at some. I've got this first one, and this is exactly in the form that we'd like, where it's one exponential function equal to another exponential function, and they both have the same base, they both have base 2, so I can conclude that the two powers must be equal, that x minus 1 and 4x minus 7 must be equal to each other. And then all I need to do now is just solve for x. So I'll bring the x's to one side, I'll bring the constants to the other, and then I can solve for x and find that my one solution for this equation is 2. The next one is not in that form quite yet. I have one exponential function equal to another, but we'll notice that the exponential functions have different bases. The first one has base 25, the second one has base 1/5. But this is where we take a moment to think about things and notice that both of these bases are really just powers of 5. 25 is just 5 squared, so the left side I could rewrite as 5 squared to the power of x minus 1. And 1/5 is really 5 to the power of negative 1. So the right side I could write as 5 to the negative 1 to the x minus 3. And now I'm just going to use my exponent properties. When you have powers raised to powers, we multiply the exponents together. So 5 squared to the x minus 1 becomes 5 to the 2 times x minus 1, or 2x minus 2. And on the right side, 5 to the negative 1 to the x minus 3 becomes 5 to the power of negative 1 times x minus 3, or negative x plus 3. And now that we've got two exponential functions equal to each other with the same base, I can say that the powers must be equal. So 2x minus 2 should be equal to negative x plus 3. And now I can solve for x the same way as before, just bringing everybody to one side and bringing my constants to the other. And I can solve and find that x should be 5/3. For this next one, we all have the same base. It's all base e, but it's not just one exponential function equal to another exponential function. On the left side, I've got two exponential functions that are being multiplied together. So what I'm going to need to do is just simplify that left side so that I have it as just one exponential function. So first things first, I have e to the power of 4 to the power of x, and I know with my exponent rules that would be e to the power of 4 times x, or 4x. And I know that if I have two exponential functions with the same base being multiplied together, that I would be adding the exponents. So to combine these two factors together, I would get e to the power of 4x plus x squared. And now I can say, good, I have two exponential functions equal to each other, both with the same base, so the powers must be equal. 4x plus x squared must be equal to 12. And easy enough for me to solve now. I'll just bring everybody to one side. And I can solve by factoring, finding numbers that multiply to negative 12 and add up to positive 4, which would be positive 6 and negative 2. And so I can come up with my two solutions. One of them is negative 6, and the other one is positive 2. So as you can see, this is sort of the nicer, easier sort of equations to solve. If we can do a little bit of work to get them in that form of one exponential function equal to each other, then we could just dispense with the bases altogether and just set the powers equal to each other and come up with our solutions fairly easily. So now let's look at some other options of what we might see. Another option is we might have something where it's one exponential function equal to another number. So depending on what our goal is, we might need an approximate solution, or maybe we want an exact solution. So what we can do is, if we want an exact solution, just rewrite it as a logarithmic equation. So if it's anything to a power of m equals n, whatever our base is, we can rewrite it as log base a. If you did need an approximate solution, and we know with our calculator we only have a button for log base e and log base 10, so if you needed an approximate solution and you didn't have the base already as e or 10, then your goal might be to do this instead. Rewrite the equation as natural log of the left side equals natural log of the right side. Because of course, if whatever we do to the one side of the equation, if we do the same thing to the other side, then we should still have something that's a true statement. And the reason we're doing that is because our property of log says when you have log of something to a power, that power can come down in front. So that would be how we would get to whatever's in that exponent that we want to be able to solve for. So we've got those two options depending on what we're trying to do. So maybe we might rewrite it as log base a, or maybe we might use a natural log depending on if we needed an approximate solution. For these questions, I'm only asking right now just for exact values only. But when we get into the next section where we start doing applications of exponential functions and logs, there we will need to come up with some approximate values. So it might be nice to know how to do both approaches. So I'm actually going to tackle these ones. The first one, I have already a base that's a nice base, base 10. So I don't have to worry about, oh, how would I find an approximate solution if I wanted to, because I know that if I were to rewrite this as a logarithm, it would be a log base 10. Before we do any rewriting, though, it has to be in the form of one exponential function on its own equal to other stuff. And that's what we've got here. We have one exponential function base 10 equal to a number, so we rewrite it as log base 10, swapping out our inputs and our outputs. And you'll notice for log base 10, as usual, I didn't write the base, I just wrote log 2, so it's understood that this is log base 10. And now I can go right ahead and solve for x by bringing the 1 to the other side. Here's just sort of a little bit about being careful with the solving. If you're bringing the 1 to the other side, a common idea might be to just write, we had log base 2 and then put a little minus 1 there, except this might be ambiguous to some people reading it. You might wonder, are the 2 and the 1 being subtracted? Are these two separate things? So to make it really clear, even though I didn't use brackets around the 2 in the first line, to make this clear that the 2 and the 1 are not being subtracted, I would put brackets around the 2 in the second line, so that whoever's reading this now knows, oh, 2 is the only number going into the logarithm, and this minus 1 is a separate term. I think maybe an easier way, though, instead of having to think about putting extra brackets in just for clarifying meaning, might be to do what I was going to originally do, which is put the 1 ahead of the logarithm. So if I rewrite that as minus 1 plus log 2, then it's no ambiguity there at all. It's really obvious 2 is the only number going into that log. And then lastly, I'm going to solve for x by bringing the 3 down. So negative 1 plus log base 10 of 2, all things divided by 3. And there we go. That's my one solution to this equation. And if I needed an approximate value, log base 10 is something I could find in my calculator, so I'm good to go with just that. Okay, so next one up, we've got something a little bit more involved. We've got not just one exponential function, but the exponential function's being divided by a number, and we've got this little -2 hanging around. So before I can do anything, I really want to get that exponential function by itself. So I'm going to bring that 2 over to the other side of the equation, and then I'll bring up the 6 to give me 12. At this point, we should ask ourselves, could I rewrite these so that these are both powers, so that these are both the same base? Because if this was a 3, then life would be good. I could say, oh, I have two things with the same base, I'll let the powers be equal. Or if these things could both be written with the same base. For example, if this number was 9 instead of 12, 9 could be rewritten as 3 squared. And so I would again have two exponential functions with the same base. But here, 3s and 12s, they're not something that can be written as powers of the same base. So too bad for me. I've got one exponential function equals to a number, and I just have to deal with it. I'm going to solve this problem twice. I'm going to solve it once, keeping the base that I've been given, base 3, but I'm also going to show that second technique where I might use a logarithm instead. So the first option, which we would have, and I just realized I miswrote my question, it was x squared, not x minus 1. If I wanted to think about solving this, I could solve it by rewriting it as a logarithm. It would be log base 3. And we would swap out our inputs and our outputs. So I would have log base 3 of 12 equal to x squared minus 1. And then all I would have to do is solve for x. And I would get two solutions. I would have the positive and the negative root of 1 plus log base 3 of 12. So I would have my two solutions in my solution set. One is positive root of 1 plus log base 3 of 12. And the other one is negative root of 1 plus log base 3 of 12. So that's one option for how we can solve it. The nice thing is it was easy enough to solve. It just did the usual, rewrite it as a logarithm and then move things around and isolate x. The downside is this, of course, you can't just plug into a calculator as it is. So if we needed to know what the approximate value for x is, you would have to be using your change of base formula that we learned in the previous section, and then you'd be able to go ahead and use your calculator to find out approximate values for x. The other option that we have might be instead of, and here I'm going to start from this line, instead of rewriting this as a log with base 3, what we might do instead is take natural log of both sides of the equation. So I might say natural log of 3 to the x squared minus 1 equals natural log of 12. I have my log rules that say log of something to a power means the power can come down in front. So I would have x squared minus 1 times the natural log of 3 equals the natural log of 12. And now I can go right ahead and solve for x. I'm going to first divide by natural log of 3 to get the x squared minus 1 by itself. And I'm going to bring the 1 to the other side. And then now I've got plus or minus the square root of all of that. And so for my solution set, I've got two different solutions. One of them is the positive root of natural log 12 over natural log 3 plus 1. And the other is the negative of that root. So here's something where we need to pause for a moment. And one thing to notice here is that even though I have what looks like radically different answers, these are equivalent to each other. We know that using our change of base formula, log base 3 of 12 is the same thing as natural log of 12 over natural log of 3. So although our answers might look different, it might look like we found two answers, then we found two different answers. Actually, the second set of answers that we found are the same as the first. They're just written in a different form. That's something that's sort of tricky when you're looking at doing practice problems with logarithms. You might come up with some sort of a solution in terms of logs, and the answer in the back of the book will look wildly different, but it may turn out that your answers are actually equivalent to each other if you just apply a couple of log properties to convert from one to the other. So in this case, we have two very different looking sets of answers, but they are equivalent to each other. Just if you were to apply the change of base formula, you could justify that, yes, log base 3 of 12 is the same thing as that natural log of 12 over natural log of 3. That second set of solutions, that would be useful if you wanted to find a decimal value. You could use your calculator to find out approximate values of those two things. So if we were solving that equation and we needed to know what's an approximate value for x, that would be a good way for us to go about doing it. Okay, and now the hardest one of all, which is, what if we have two exponential functions and they have different bases? So we have one exponential function base a, and we have another exponential function base b. So there's a couple of options actually what you could do. The one that will always work is to just take natural log of both sides like we did before. And that means that we'd be able to take our exponents down in front, just like we did before, and then solve for whatever was in our exponent. That's, of course, one option. But the other option might be, instead of using natural log of both sides, you might use a log with a different base instead. So, of course, the obvious choice is here, since one of our exponential functions is base a, you might decide to take take log base a of both sides. Or, since the base of another one of these is b, you might decide to take log base b of both sides. Of course, if you're using natural log, that means that'll give you an answer that you can plug into your calculator and get a decimal value if you needed it. But if you're looking for an exact value, it actually might be faster or easier to use log base a or log base b instead. I've got a couple of examples, and I'm going to do one of them with natural log, but I'll do the other one with the base as it is. So first one's first. We have a 3 to a power equals a 2 to a power. And we should always ask ourselves whether we could rewrite these bases so that they're both powers of the same thing. So if this had been 4 to a power and 2 to a power, we'd be easier and happier if we rewrote 4 as 2 squared, and so that we'd have 2 to the power of for both exponents. But we've got 2's and 3's, and so too bad for us, we can't rewrite those as powers of the same base, which means we're in that special case where we've got two different bases. So what we're going to do is, just like we did for the last problem, I'm going to take natural log of both sides of the equation. So natural log of the left side equals natural log of the right side. And just as before, those exponents will come down in front. One thing to note here, just you might have noticed me putting brackets around that exponent. That's really important, because if I had just brought my power down and said 3x plus 1 natural log of 3, it would look like only the 1 and the natural log of 3 are being multiplied. And that's, of course, not true. The entire power needs to be multiplied by that natural log of 3, which is why I need brackets around it. Same thing for that 4x minus 1. I need brackets around it as well, because all of that needs to be multiplied by that natural log of 2. Okay, so next thing, I'm going to just expand what I have on the left side. So 3x times natural log of 3 plus 1 times natural log of 3. And on the right side, 4x times natural log of 2 minus 1 times natural log of 2. And now I'm just going to go ahead and start solving for x. I'm going to bring everybody with an x to one side of the equation. So 3x natural log of 3 is on the left, and I'll move the 4x natural log of 2 also to the left. And everybody else I'll move to the right side. The negative natural log of 2, that's on our right side, and the natural log of 3 I'll move to the right side as well. And now I can see that on the left side I've got two terms. Both of them have an x as a common factor, so I could take an x out as a common factor and be left with 3 times natural log of 3 minus 4 times natural log of 2. And then I can go right ahead and solve for x by dividing, and I'll have my solution. Okay, so I can say that my solution to this equation is the number negative natural log 2 minus natural log 3 over 3 natural log of 3 minus 4 natural log of 2. I could stop there, and I'm totally fine with you stopping there, but I will point out that there are ways that we could simplify this answer and make it a little bit more compact if we wanted to. So all of what I'm going to do here on the right, this is completely optional, but if you wanted to sort of see how other people might write their answers, or specifically how you might see the answer actually given in a textbook, it's good to sort of think about what I'm doing here. First thing, if it was a textbook answer, textbooks generally don't like to have this many negatives lying around, so the first thing that they would probably do is multiply top and bottom by -1, so that you'd have a positive natural log of 2, a positive natural log of 3, the 4 natural log of 2 would be positive, and the natural log of 3, the 3 natural log of 3, that would be negative. The next thing that they might do would be to start using some log properties. On the top, you have natural log of 2 plus natural log of 3, which becomes natural log of 2 times 3, which is natural log of 6. On the bottom, we have 4 times natural log of 2. That 4 can come up as a power on the 2. Same thing for 3 natural log of 3. The 3 could come up as a power on the 3. And if I just evaluate that quickly, 2 to the power of 4 is the same thing as 16. And 3 to the power of 3 is 27. And finally, I have in the denominator 1 natural log minus another. I know that that's going to give me natural log of a quotient, natural log of 16 divided by 27. So instead of giving the answer as I originally did, I could give my answer as natural log of 6 divided by natural log of 16/27. This is, again, what I meant about how with a logarithm, your answer may look wildly different. And in this case, it's not even slightly different, it's completely different. The original answer that I had a bunch of 2s and 3s and 4s, and here I've got 6s and 16/27. It looks like a completely different number than the first one. However, these two answers are equivalent to each other. So that's why when I say if you're looking in the back of a textbook someday and you're solving an equation and there's a log in the answer, if your answer looks wildly different from theirs, stop and ask yourself if your answer could be turned into theirs with some log properties. So in this case, what I have here, with a little bit of extra work, I'm able to make it slightly more compact and come up with 1 natural log divided by another. And again, it looks like a wildly different answer, but it is equivalent to the first. Again, I'm not expecting you to do this sort of work. So if you stop here, that's perfectly fine, and I am 100% satisfied with what I originally came up with in black as my answer. And if you came up with that, I would be happy with that as well. So this one we solved with logarithms, but we could have used log base 3, or maybe we could have chosen to use log base 3 instead on both sides, or chosen to use log base 2 instead on both sides. I'm going to do that with a different example. So again, we're going to have something where we've got two exponential functions, both with different bases, base 4 and base 5. There's no way I could rewrite these as both powers of the same base. So if it was 4 and 16, or if it was 25 and 5, then I could do that. But here I'm stuck with two very different bases. And I could do, if I wanted to, the whole natural log business. So I could start off by doing natural log of 4 to the x minus 7 and natural log of 5 to the x. And that would definitely get me to a correct answer. But I might instead decide to say, if I'm not looking to find a decimal answer for this, if I just want the exact solution, what I might choose is log base 4 or log base 5. And I'm going to use log base 4. I'll take log base 4 of both sides. And same as before, powers will come down in front. And one thing that we'll have, which is kind of a nice thing, log base 4 of 4, that's just a number. 4 to what power gives us 4? The answer is the power is 1. So really the left side is x minus 7 times 1. Or in other words, the left side is really just x minus 7. That's one of the strengths of using one of the two bases that's in the equation. If I use log base 4, then the 4 to the power of will be gone and I'll be just left with that power. If I had chosen to use log base 5, then the 5 to the power of would be gone and I would have just been left with the power x. So it makes it a little bit more compact as far as the amount of symbols you have to work with. Here, I'm going to solve the same way that we did before. I'm going to bring all the x's to one side. Bring the numbers without x's to the other, or terms without x's to the other side. I will factor out that x. There's an x that can be taken out of both terms. And then I'll solve by dividing. And so now I've got my solution, and my solution is 7 divided by 1 minus log base 4 of 5.